In part 2 we're going to use our calibration that we've prepared in part 1 to make some measurements, and I'm going to include in that a little explanation of some trace discontinuities that we see when we've used a TRL and TRM calibration. We'll look at an optional adjustment for compensating those, and then we'll make measurements of some on-substrate devices under test, and get a chance at the end to compare TRL, TRM calibration with that of a salt calibration. Well, we're now in a position to make some measurements, but I'm sure some of you, certainly people that are not familiar with TRL calibration, would be a little bit worried about the discontinuity in the trace we see at the moment. We're measuring these two loads, so those two mismatch plots, S11 and S22, not exactly what we expect to see. Might be what we expect to see if you are familiar with TRL, but let me, for those that aren't familiar, let me try and explain. And I thought the way I'd do it is first of all to change these two loads, and we'll put a couple of known good loads on these ports. So these are normal calibration standards from a short open load and through kit. They are of a very high quality, so we're going to expect to make a fairly good 50 ohm measurement with these. Let's replace that. Put the slightly longer one on port 2. And we'll put this one on port 1. Okay, now, so if we look at the plot now, we do still have a small discontinuity. Now, before I started recording this video, I measured these two standards with a normal short open load calibration. I used our new ecal module, calibrated at these two PC 3.5 ports. And got ourselves a reference measurement for these two loads, and we can see it there in the slightly yellow trace that I've added there. So we've got a fairly reasonable measurement of these two 50 ohm loads, but we've still got a discontinuity in the trace here and here. We're certainly not picking up this this dip into good match here that is measured using a normal calibration. And why is that? Well, the explanation comes about because these two calibrations, this is the calibration resulting from using the line as our calibration standard. This is a calibration resulting from using the 50 ohm resistors, or near 50 ohm resistors, the TRM match loads on our board, and this is a calibration using a known good 50 ohm, characterized 50 ohm in an ecal unit. They're all different calibrations, and the TRL and the TRM, so this is the TRM section, this is the TRL section, these two, the line and the resistors, do not quite match each other, and so we get this discontinuity here, and neither of them are exact matches for the 50 ohm, so we don't match that yellow trace there. let's look a bit further at this. Let's now go back and measure our TRM loads using the TRL calibration, or TRM and TRL calibration that we just performed. So let's take these off. We'll reconnect these two TRMs. Let's look again. Behave yourself, Mark. Sort things up properly. Okay, so we've reconnected the TRM matches, and not surprisingly, we've got our very big discontinuity back. And the reason for this, so this TRM section, we are measuring the TRM loads on the board using a calibration that was based on the TRM loads on the board. In other words, we're measuring the calibration standard. And so we're getting an exceptionally good match here. Here, we're measuring the TRM loads with the TRL calibration as standard. Now, that clearly isn't going to be quite such a good match as measuring the standard with its own calibration. So we've now got this large discontinuity, and we would expect it. Let me move the let me save that to memory. So I'm saving the blue trace now to the memory trace. Okay, so they're out of lane now, and then we'll move our measurement to the line. Go. Oh, goodness me. So now what we're seeing, the TRL line measured at low frequency using a calibration that was based on the resistors on the board, the TRM resistors. Here we are measuring the line with a calibration that was based on the line as a standard. So once again, we are measuring the line with its own calibration. So clearly here, match is going to be exceptionally good. Here, we're getting a fairly reasonable measurement for the resistors, and you can see there's a join here. There won't be a join here, but there is a join. in the blue trace and the yellow trace here. So this is how these discontinuities come about, and they're each section of the TRL calibration is based on different standards, and so you're bound to get discontinuities, and you'll particularly get discontinuities if you're measuring one of the standards that was used in the TRL calibration. Okay. So I think the important takeaways at this point are that the TRL TRM calibration, using the standards on this board, that did not impart any knowledge of what a known 50 ohm match looks like. We didn't use a characterized 50 ohm load at any point. So this calibration, this TRL TRM calibration, doesn't know anything about true 50 ohm, and certainly not a true 50 ohm placed on the substrate at the reference plane that we wish to use. Instead, we used load resistors that are in the right place and should be fairly good, placed on feed lines that have been measured to closely meet design intent. In other words, even the feed lines aren't exactly 50 ohms. They are as close as we could make them, probably designed in a CAD environment and then transferred onto an FR4 substrate, which, as we know, can be rather variable. So we have on the board we have two reasonably good standards. We have a reasonably good line, and we have a reasonably good pair of resistors. They make reasonably good calibration standards, but they are not true or very well known 50 ohm, nor do they accurately match each other at the frequency where we cross over from TRL to TRM. And thus we have these self-measurements above with discontinuities, stepping from close match to excellent match, or vice versa, excellent match to just a close match. And if we return to those earlier measurements that we did of the known good SMA loads, we measured them with TRL and TRM calibration, blue, and ECAL calibration at the SMAs, yellow. We have a degree of match between the two results, but we have to remember that the TRL TRM calibration, firstly, is not calibrated at the correct SMA reference plane for these connectorized components. It's also a calibration based on two separate Z0 values that do not exactly match 50 ohms or each other. Hence, the blue trace does not exactly match the yellow, and the blue trace has a discontinuity at the interface of the TRM and TRL bands. And by the way, if we had used two TRL line sections, we would now have another frequency band and a further discontinuity as well, although in practice that would probably be a rather smaller discontinuity between two different line lengths. Now, as an aside, I did mention very early on that TRL and TRM calibration can in fact be very, very accurate indeed, and I mean for a calibration at Z0, which is 50 ohms. And the reason for that is that it is actually possible to machine a precision airline of very precise dimensions that you know to be a very good 50 ohm impedance. And we can make fairly good loads TRM sections as well. So in fact, TRL TRM calibration can be, in a high precision environment, even more precise than the use of salt kits as we most typically do. Of course, these precision airlines are extremely expensive devices, and we typically don't use them, but not for working standards. But let it not be said that TRL, TRM is necessarily less accurate as a 50 ohm measurement. It's far from the case. But certainly when we're measuring standards on a piece of FR4, it's not going to be quite so good. Okay. Can we do anything about this discontinuity? Well, let's see. There we have our measurement of line referenced by the two standards, the TRM and the TRL. Can we do something about this discontinuity should we wish to do so? Well, yes we can. We can use the enhancement menu here to make an adjustment of the TRL line impedance. And here we see we have two lines because the VNA supports a two-line TRL calibration. We've only used one, so we're going to use one here. Let's close that for a moment. And what I'm going to do, I'm going to measure this point here with the marker. So this is our line measured with our 50 ohm resistors as the calibration standard. And if we look on the Smith chart result at marker 1, put glasses on, we get 49.43 ohms and 1.12 reactive component there. So let's go to the enhance menu and put in here line 1, 49.34 ohms and 1.21. Apply. Oh my goodness, there we go. We've got rid of our discontinuity altogether. But what have we just done? We've just corrected the line measurement to be the same at this frequency as the load resistors, or as the TRM resistors. It gets rid of our discontinuity, and we may wish to do this, but that may not be a better measurement for the application that we're doing. So some users will want to make these sort of corrections, and can, using our software, but it's not necessarily the right thing to do. Okay, let's leave that in place. We're now going to use our TRL TRM calibration to measure a couple of dots. So dot number 1, device under test number 1 for this board is a bandpass filter. It's a pretty standard mini circuits component, and certainly if we wanted to verify this component against its specification, we would need to make a measurement that is referenced right at these two contact points with the board, and that's precisely what we're now able to do. So let's have a look at this. We need to adjust the sensitivity on S21. We can move this to get a bit more sensitivity on there and a bit more on this one. So bandpass filter measured using TRL, TRM calibration. So I thought it'd be interesting to make before starting the video, to make the best measurement I could of this device on this board, but using a calibration at the PC 3.5 reference planes. So I did that, and we'll just load that data. Load measurements. So I'm loading this long named file here. So this used e-calibration, reference plane shift, and normalization. In fact, I used a simple normalization at 1 gigahertz to make a measurement based on an e-calibration of the PC 3.5 planes. Open that, close, and there you are. There's our comparison with the two sets of data. And actually, the TRL TRM calibration is going to be a little bit better for us here, because my normalization for the feed lines was pretty crude when I made the measurement using eCal. That's the measurement in yellow. Nevertheless, very good match. Let's see if this enhancement makes any significant difference for us in these measurements. So if I untick that and apply it, there we go. That has applied, believe it or not, but you can't see any significant discontinuity in any of these plots on this particular measurement. It's not making a great deal of difference for us. Okay, let's try another type of dot. The other dot that I've got on this board at the same reference planes is a -6 dB attenuator device again from Mini Circuits. Let's see what we're doing with that. So this should be very good. 50 ohm match. Oh, here we go, look. We can see that measurement of S11 and S22 both got a small discontinuity in them. Let's reapply. You can see the discontinuities have changed, but I haven't been able to eliminate them with this type of correction altogether. So yes, we do have a discontinuity in our match measurements, but we are down below -35 dB, or down in that region with the discontinuity. So it's not going to upset us a great deal. Let's load the correct data for this. Because likewise I measured this using an e-calibration and reference plane shift and normalization. I'll load measurements. Not so good. So this calibration does not match, or this measurement with eCal doesn't match as well as we might hope. But I've only used reference plane shift and normalization in here, so neither of those corrects for match. So this measurement was made inclusive of the feed lines as mismatch and as loss. I've tried to compensate the loss and the phase delay of the feed lines as best I can, but I haven't compensated the match the feed lines, and that's why this measurement is not so good. This measurement will be the more reliable measurement of the match on this measurement here of the two matches. Let's have a look at our S21 with a bit more resolution. What do we need here? Let's go to, I'll go to 0.5 dB and re-reference it. -6 in there, and let's pull that down, and there we go. So we're measuring S21 fairly well. We do have a little disagreement here. What's that? That's of the order of 0.3 dB. This will be because my normalization in the ecal based measurement is not that good. I really should have done a de-embed of the lines to get closer to my TRL, TRM calibration. And there you go. Let's just get rid of that ecal result, you can see we have a fairly good result here. Let's have a look. We've got the enhancement on. Let's just turn that off. See if that changes our measurement on S21, and no, it doesn't. It does affect our S11 and S22 slightly, but not S21 here. Okay, so I hope that's given you a little bit of insight into TRL and TRM calibration for a device mounted on a substrate. Thank you. Thank you. As a footnote to this demonstration, I think we have seen here that TRL-TRM calibration results in bands of calibration that each have slightly different Z0. Those Z0s might be very precisely 50 ohm if we are using airline standards, but more likely, if we're using substrate-based standards, they may each be slightly offset from 50 ohm and from each other, and that might be imaginary offset or real offset. In other words, our Smith chart will have slightly different origins for each frequency band: TRM, TRL line 1 and TRL line 2 if we are using two lines. The resulting discontinuities, here very large, we were able to correct to an extent, thus. But even here on the right, S22 not quite as well corrected as S11. In effect, we used a single correction based on port 1 to correct two ports using different TRM match resistors and two ends of a line that are slightly different via two feeds that are slightly different. All of the components have finite differences and can't really be corrected by one single correction. And then we went on to look at a very well matched second DUT, the attenuator, and saw a discontinuity again, albeit at very much better level of match. All that said, our TRM TRL calibration gave a better result than the SALT calibration plus reference plane shift, and was more convenient to achieve. It only suffered from a trace discontinuity at very good degrees of match. Levels not likely to worry us on this FR4 substrate.